Hey everybody. Okay, there's a lot going on here, right? A lot happened in the early universe to create the universe that we live in today. Um, I don't need to go over all of this, right? You read all of this, so let's look at the practice problems here. Um, all right. Sort the following into whether they happened before or after the first 20 minutes of the universe. So let's refresh our memories here, right? What happened in the first 20 minutes of the universe? Well, the Big Bang happened, right? The universe was filled with just energy and subatomic particles. And then, in the first 10 billionth of a second, right, the universe expanded and cooled off so that it could inflate and flatten out really quickly. After 3 minutes, the universe had cooled off to the point that protons and neutrons existed, and then the hydrogen and helium could start fusing. The antimatter got annihilated with most of the normal matter, and then after 20 minutes, the universe fully cooled off enough and expanded enough that the particles were too far apart and not moving fast enough that the fusion slowed to a stop, essentially. Leaving us, after that 20 minutes was done, the universe was hot enough, long enough, for the universe to turn into 25% helium, and the other 75% was the hydrogen that formed at the very beginning. Right? So that's what happened in the first 20 minutes. Right? When were stars born? Well after that, right? After 20 minutes, the universe was just a hot plasma of hydrogen and helium, and it took another, the oldest stars and galaxies that we can see far away started being visible about 700 million years after the Big Bang. So it took like 700 million years, thereabouts, for the first stars to be born, at least so that we can see them in our telescopes. So, yeah, well after 20 minutes. The first galaxies created, again, well after, right? It took a long time for after 20 minutes, the universe was just a hot plasma of hydrogen and helium, and the universe needed to keep on expanding, cooling off until eventually gravity could pull mass together into the first stars and galaxies. That took a long time. When was the universe expanding faster than the speed of light? Well, that was that inflationary period, right? At the very beginning, when the universe expanded really quickly and spread all the matter and energy out fast enough that gravity didn't have time for it to clump up into big, dense clumps early on, right? That era of inflation was in the first fraction of a second after the Big Bang. When was the universe fusing hydrogen into helium? That was right before the 20-minute mark, right? From 3 minutes to 20 minutes is when the very first fusion was happening. Right after the Big Bang. Right? After 20 minutes, the universe cooled off, the fusion stopped, and then fusion wouldn't start up again until stars formed hundreds of millions of years later. Almost all the matter and energy annihilated. Again, that was well before, right? That was early on, when most of the antimatter got annihilated with a lot of the matter, and the universe that we live in today was all of the matter that was left over after the matter and antimatter annihilation was done. When did the cosmic microwave background form? Well, that cosmic microwave background, that formed when the universe expanded enough and cooled off enough that the gas in the universe could neutralize and become transparent, right? The universe, before the cosmic microwave background was produced, the universe was so dense and so hot that it was opaque. It looked like the inside of a star. And then eventually, after 380,000 years, right? It took 380,000 years for the universe to cool off enough that the gas could neutralize, become transparent, and then the universe became full of a transparent gas that could let this light shine through it, and that light has been shining through the universe ever since for us to see it today. But that took 300,000 years, well after the 20-minute mark. All right. What will the fate of the universe be? Well, the fate of the universe depends on the density of matter, the density of mass. What will it take for the universe to collapse back on itself? Well, you would need to have a density that is greater than the critical density. Right? If the universe expands forever, but it never slows down to near zero. Sorry, folks. Somebody came in my office and I had to pause the video for a minute. Okay, where were we? Yeah. If there is enough density in matter and energy, then that density of matter will exert enough gravity that it can slow, stop, and reverse the expansion of the universe, so that if the density of matter in the universe is greater than the critical density, then that leads to a universe that will eventually recollapse on itself. If there is less than the critical density, then that means there isn't enough density in matter and energy. There isn't enough gravity in the universe to slow down the expansion of space-time, and therefore the universe will keep on expanding faster and faster forever. The critical density, the definition of the critical density, is a universe where the universe is expanding, but gravity will slow down expansion, but not enough. That as the universe expands, gravity will slow it down, but never reach zero. The expansion of the universe will never reach zero, except at an infinitely long time span. Because if the expansion of the universe ever stopped, then gravity would start pulling everything back together. It would eventually recollapse. That is a universe where density is greater than the critical density, right? The definition of critical density is one where the universe keeps on expanding and slowing down, but never actually stopping. So which universe do we live in? Well, we live in a universe, we definitely know for sure that we don't live in a universe that is slowing down. In fact, the dark energy suggests that the universe is actually speeding up in its expansion. And so it's one of these two, right? The universe, there isn't enough density in the universe, even taking dark matter into consideration. Even with the dark matter, there isn't enough mass to cause the universe to recollapse. So we're either living in a universe that's going to keep on expanding forever but slower, or a universe that is going to keep on expanding forever but faster. And the discovery of the dark energy seems to be suggesting that the universe is going to keep on expanding, but faster and faster and faster. So ultimately, we're not in a universe that's going to recollapse in a big crunch. We're not in a universe that is static and unchanging. We're living in a universe that will keep on expanding, keep on cooling off forever. So there you go. It sounds kind of a downer. But that is the best explanation that we have today. Again, that explanation depends on what we think we know today about dark matter and dark energy, because dark matter contributes to the density, and dark energy causes the expansion to speed up. So once we have better understandings of what dark matter and dark energy are and where they come from, then we'll have a better understanding about what is the critical density, what is the density of our actual universe, and then what the ultimate fate is. But all of the measurements that we've made for the last 100 years sure make it seem like there just isn't enough density, and that we're either living in a universe that will keep on expanding but slow down, or keep on expanding and speed up. Either way, a universe that ends in the heat death. That sure is the ultimate fate of the universe as far as our best explanations have seen so far. But again, that's based on the evidence that we have. Who knows what tomorrow brings? That's what keeps this all so exciting. Okay. I hope that makes some sense. And we'll move on from there. All right. Have a good day, everybody.